All right, so this is section 9.2, part 3, and this will be our final part for this section. And we've actually already covered all of these concepts. We've talked about how the best point estimate for a population mean is the sample mean, x bar. We've seen how to construct a confidence interval estimate for a population mean with data. That was in our last section. Now we're going to do it, what if we have statistics? So that's going to be for this section. And then we will interpret a confidence interval again, and we saw the required sample size needed in the previous video. All right, so as I said, this is an example with statistics. So a random sample of 50 recent college graduates results in a mean time to graduate of 4.58 years, with a standard deviation of 1.10 years. This is based on some data gathered from the U.S. Department of Education. So the first thing we want to know is, are all of our conditions met for us to use the t-distribution and the t-interval function? So I've got those listed on the next page so we can check and make sure that we'll be able to use t-interval. All right, so first of all, we want to make sure we have a simple random sample or that our data came from a randomized experiment. In this case, we do have a simple random sample. We were told it's a simple random sample of 50. So next is our sample size. So remember, n equals 50. Is that no more than 5% of the population size? Well, if we think about recent graduates, I think we can assume that 50 is a very small portion of all recent graduates. And then thirdly, so we can make a check mark there, we want to know that it's normally distributed without any outliers, or that it's a large sample size. Well, we have no idea what this distribution looks like. We're not told that it's normally distributed, and there's no indication of the shape at all. But we do have a large sample size. So remember, we needed n to be greater than or equal to 25, and in fact, since n is 50, we've met that condition. So we can use our t-interval for this problem. Great, so now we want to know. Let's actually compute and interpret a 90% confidence interval for the mean time to graduate with a bachelor's degree. So again, we have statistics this time. So we have an x bar, a sample mean of 4.58 years, and we have a sample standard deviation given to us of 1.10 years. We're going to use that in with our t-interval, and we're going to go to that stats option instead of data and find our confidence interval. All right, so I've written down our statistics given to us, both our sample mean, sample standard deviation, and sample size given to us on the previous page with our problem written out, and we're going to use these along with our calculator to find the confidence interval. And so if we go to tests down to number 8 for t-interval, again, we don't have data, so we need to go over to stats. And of course, just by going over to the statistics, that doesn't change anything. We must hit the enter button to select stats. And we actually see our information, if you did the problem with me, from the previous problem. So that's our mean and standard deviation and sample size from part 2. We're just going to type over that. Those are just the currently saved values for those variables. So we're going to go down to our sample mean, and we're going to type in our new value. .58, our standard deviation, 1.10. And then, of course, our sample size has changed to 50. And we're not doing a 99% confidence interval anymore. We're going to be doing a 90% confidence interval. So we're going to make sure we change that to 0.90. When we press calculate, we'll get our interval. And so here we have 4.3192 to 4.8408. So there's our confidence interval for this problem. Of course, interpreting it helps us put this answer in context. What do these numbers actually mean? Well, so we have to remember that we were doing a 90% confidence interval. So we can start off by saying we are 90% confident that the mean time to graduate with a bachelor's degree is between 4 and I'm going to go ahead and round just to one decimal place, 4.3 years and 4.8 years. Now, with this rounding, of course, follow along with whatever my Lattice Plus tells you to round to, but also make sure you don't round too much. If these both round to the same value, as far as if we went to one decimal place, if these happen to both be the same value, that wouldn't no longer be an interval. So we would need to take it out to an additional decimal place. In this case, to one value, to one decimal place gives us different numbers. All right, so our next part of this question asks us if this evidence, so this confidence interval that we found, does this evidence contradict the widely held belief that it takes 4 years to complete a bachelor's degree? And of course we see our interval, I've written it up at the top here. This is where we want to know, is 4 within our interval? 4.3192, that is our lowest possible value according to our data. So this does contradict. So this confidence interval contradicts the idea that a bachelor's degree takes 4 years to complete. And the reason for that is because, so I guess I can make that into a comma, because 4 is not within our interval. Now, we also can't say that it should take 5 years to complete. So it's somewhere between 4.3 and 4.8, as we said on the previous page. But it's, 4 is a little bit quick compared to our sample, and 5 is a little bit slow compared to our sample. But that's how we can use this information. We can actually answer questions about this idea of a 2-year degree and a 4-year degree. We call them those, but an associate's degree and a bachelor's degree are typically take longer, and especially now because so many students are not just going to school. I know many of you have families that you're taking care of. You have jobs. You probably have, some of you I know have more than one job, and you're trying to come to school and do this work, and it's going to take you longer to finish a degree because you're not taking 5 or 6 classes every single semester. And really, in order to complete one of these degrees, an associate's degree or a bachelor's degree, in the that time frame of 2 years or 4 years, respectively, you've got to take 15 hours each semester, or catch up with those extra hours in the summer. And that's not easy to do when you have other responsibilities. When I went to college, I didn't have anything but to go to class. I did have a job, if you can count it as one, where I worked at a daycare for 3 hours in the afternoons, Monday through Friday. And I basically sat there and worked on my homework and made sure that the kids at the daycare didn't kill each other. And, other things too. But for the most part, it was not strenuous. I was able to do my work while I was there. So I don't count that as having extra responsibilities. I was fortunate to just be able to go to school and only focus on school. But that's not the way most students are now. Even students going to 4-year universities, many of them are not only going to school. They're working to help pay for tuition, room and board, gas money, whatever. And then many people are going back to school after they've started a family and they have kids to take care of. So, these numbers, these 4-year degree and this 2-year degree title, really aren't accurate anymore. And so that's a very long monologue there for this problem. But this is how we can see how things change. How are trends changing? How are things different from 20 years ago to now? And we can use it with statistics. All right, so this next part, we're going to use the information that we just found. So this 90% confidence interval that we found on the previous page. And we're going to see, what happens when I change the confidence level. I have the same information. I'm using the same sample mean, the same standard deviation. But I want to be 95% confident instead of 90% confident. So 90% confident sounds pretty good. That's a 10% chance, though, that you've got something wrong. And so 90% of the time, my interval is going to include the population mean, but 10% of the time it won't. I would like to have more confidence. So I'm going to be 95% confident. And when I do that, and I've got just a screenshot of our calculator for this rather than the actual video of it, because if you need to see how we get the confidence interval, then just go ahead and rewatch the video or the previous few pages back. But for now, let's see if I can fit both of these on here. Right there, that should be pretty close. There we go. So the only thing I've changed, and I'm being extra crazy about how lined up this is, but oh well, I'm just gonna leave it. So the only thing, if you notice, the only thing that I changed was I made this 95% instead of 90%, but I still have the same mean, same standard deviation, same sample size. And if you notice, my confidence interval is now 4.2674 and 4.89 to something, 26. There's a part of my controls for my whiteboard are kind of covering that up, but I think that's right. So there is my confidence interval. If I'm 95% confident, then my interval is, if you notice, is a little bit wider. And so if I were to be 99% confident, in fact, I think I'll go ahead and put this in my calculator real quick and see what happens. If I'm 99% confident, same data, same sample size, everything else exactly the same, then I do get closer to that 4 years, but I'm still, with 99% confidence, I am still not getting Interestingly enough, I'm not getting 4 in my interval or 5 in my interval, although that is really close, and we could nearly round that up to 5 years. But notice that each time I increase my confidence level, the width of my confidence interval increases. So that's one way to affect the width of a confidence interval. The bigger my confidence level, the bigger my interval. All right, so that's what we call a direct relationship in mathematics. And you may remember that if something goes up as another value goes up, then they are directly affecting the outcome. This next one is different. So let's say that we have our normal data, a random sample of 50 students, and we got this mean and standard deviation. But let's suppose we came up with the same mean and the same standard deviation for a sample of 100 recent college graduates. Now, obviously, this is not something that we would normally see. We've heard time and time again, samples vary. But just to see how sample size affects the width of a confidence interval, let's just assume everything else is the same. Only change one value. We're going to keep it the same confidence level. We're going to use the same mean, the same standard deviation. But now, instead of 50 recent college graduates, we're going to look at 100 recent college graduates. So let's take a look and see what that gives us for our confidence intervals. All right, so once again, here's our confidence interval that we found back in part B for a 90% confidence interval when we had our sample size of 50. If we do a confidence interval and the only thing we change is our sample size, and so let me again bring these screenshots of the calculator up, then we notice, again, the only thing I'm changing, the only thing that's different is my sample size. I still have the same sample mean, sample standard deviation, and I'm still dealing with a 90% confidence interval. But now my confidence interval does what? Well, have 4.3974 and 4.7626. So these numbers are closer together. This has essentially made my confidence interval smaller. So if I have a larger sample size, then even with 90%, I'm still 90% confident, but I've narrowed in a little bit more. If I change that to 1,000, so I don't have a screenshot for this, but I'm just going to test it really quick. So I've got all my same mean, same standard deviation, but I'm going to say 1,000, a sample of 1,000 graduates, and I want to be 90% confident. Then I really narrow down. So a 90% confidence interval when n equals 1,000 is going to be 4.5227 up to 4.6373. So notice that is really narrowing in on how long this will take. So there's lots of ways. Now, just imagine, what if I increased my confidence level and I increased my sample size? Then I'm really going to be able to come up with an interval estimate that can help estimate what that population mean or population proportion, because the same effects will happen with our confidence interval for a proportion as well. I can really pinpoint and narrow down that range of values for our population parameter, regardless of what it is.